In the last video we had seen the introduction of electric field lines, and the most important that we come to know the forces which are non-contact are actually applied with the help of field lines. That's why every charge which apply electrostatic force produces the electric field in its surrounding. Any magnet which can attract an iron nail produces magnetic field in its surrounding. Any mass or material such as earth apply gravitational force, and earth produces gravitational field in its surrounding. So overall, the conclusion, the non-contact forces are always applied with the help of field lines. Today we will see the properties of electric field lines. So just you see, we will keep it very simple. So here you can see the properties I have written. Split, S-P-L-I-T, split, AC. So in the last video already I had told that we will study the properties of field lines with the help of air conditioner. So here the split AC. Now just you focus on these terms. These are the properties of electric field lines. S stands for electric field lines starts from positive and terminate at negative. P stands for electric field lines are perpendicular to the surface of conductor. L stands for greater the line density of electric field, greater the electric field strength. That is, if the line density of electric field at a point or in a space is greater, so the intensity of electric field also will be greater. I stand for intersection free, that is, electric field lines never intersect each other. T, the direction of electric field at a point can be obtained by using a tangent at that point. That is, T stands for tangential direction. A, electric field lines apply forces only on the charges. So electric field apply forces on the charges or on the charge bodies. C, electric field lines are a continuous but not a closed curve. Now we will elaborate these points. First, start from positive and terminate at negative. Now let's see. This is a positive point charge, and these are the electric field lines. All these electric field lines are starting from positive, and due to a point charge, the electric field lines are always radially outward. So radially outward direction, the electric field lines are emerging out. For a negative point charge, all the electric field lines are terminating at the negative charge. What happens if there is a system of positive and negative charges? If there is a system of positive and negative charges, so electric field lines will start from positive and they will terminate at negative. You can see these curves are starting from positive and terminating at negative. What about this line? This line is starting from positive. It will go up to a long distance, then it will come to the negative and it will terminate. What about this line? This line is starting from positive, going to the infinity, and again coming back from the infinity to terminate at negative. Now, second point, P. Electric field lines are perpendicular to the surface of conductor. Now just you see, This is a charge which is a source of electric field, and these are the electric field lines. This is a conductor. Now these electric field lines are perpendicular to the surface of the conductor. These electric field lines here are perpendicular. Now these are emerging starting from positive and falling on the surface of the conductor perpendicularly. Inside the conductor, net electric field is always 0, and then again they will continue from the opposite face of the conductor. That is, electric field lines are absent inside the conductor. Now, this is a rectangular slab of metal, and this is a positive charge kept in its vicinity, means nearby this conductor. Electric field lines starts from positive, and they will fall on the surface of conductor perpendicularly. They are falling. As I told, inside the conductor electric field is 0. So from the opposite face the electric field lines are re-emerging and moving. Remember, these are perpendicular to the surface every time. This is a metallic sphere, hollow sphere. This is the thickness of metallic sheet. At the center of this metallic sphere, a point charge, positive point charge is kept. So this positive point charge will emerge the electric field lines. These are the electric field lines. All these electric field lines are radial, so these field lines are falling on the metal surface normally. Again, inside the metal, inside the conductor, electric field is absent, net electric field is 0, so they will re-emerge from the outer face or further face of the conductor or sphere. These are. Again, there is another sphere, but here the location of the charge is not at the center. This is the metallic sphere. Point charge is kept, but not at the center of the sphere. It is kept nearby the boundary of the sphere, nearby the wall of the sphere. Electric field line will start, but this will follow the agreement that electric field will fall on the metal surface perpendicularly. So these field lines are falling on the metal surface perpendicularly, and again as it is, they will emerge out from the metal surface perpendicularly. The electric field lines will come out of the surface perpendicularly. Now just you see the difference in these two diagrams. Here the positive charge is at the center, so electric field lines are radial and outward. Here the charge is not at the center, and in spite of that the field lines will fall perpendicularly on the surface. So this was the second property, that electric field lines are always perpendicular on the surface of the conductor. Third, L, line density. Greater the line density, greater the strength of electric field. Here these are the field lines due to some charges or system of charges. At point A, the line density is, just you see the line density. Line density means number of lines, electric field lines passing through unit area. So here across this unit area, if I take this both the loops of equal area, so here there are the 3 lines passing through this much area, and here only the 1 line is passing. So here it is the point where the line density is stronger. So at this place electric field intensity is more than that of electric field intensity at B. Similarly, if we see at these 2 points, at this point and at this point, if I draw a loop of the unit area. So here 1, 2, 3 field lines or more than 3 field lines are passing, and at this point only the 2 field lines or less than 2 field lines are passing. Therefore the electric field intensity at this point, say this is X and this is Y, electric field line at the X is more than the electric field line at Y. Now I, intersection free, that is the 2 electric field lines can never intersect each other. Suppose that this is a pattern of electric field lines I have shown due to a system of positive and negative charges. Here the electric field lines are intersecting each other, as well as here the electric field lines are intersecting each other. So what will happen if the 2 electric field lines will intersect at the same place? At the same point, if the 2 electric field lines are intersecting, it shows that you can draw the 2 tangents at a place. Here you can draw the 2 tangents at the same place. It will show you the 2 different directions at the same point, which is not possible. Therefore the 2 electric field lines can never intersect each other. Now here I have drawn the pattern due to some system of charges. Now here you can see the 2 field lines are intersecting. It means this is also the direction of electric field, as well as this is also the direction of electric field. At a point there cannot be the 2 direction of electric field. That's why the 2 field lines can never intersect each other. T, tangential direction. Suppose that this is the electric field due to some system of charges. This is the pattern of electric field. This is a point P. Here I want to know what is the direction of electric field. So I will draw a tangent at this place, and this tangent will show the direction of electric field. Similarly, if I want to know what is the direction of electric field at this point R, so I will draw a tangent at this point, and this tangent will show the direction of electric field. Suppose that this is a point M. I want to know what is the direction of electric field at this point. I will draw the tangent, and this tangent will show the direction of electric field. So the direction of electric field can be determined by a tangent at the point. Now A, apply forces. What does it mean? In the definition of electric field we had seen the electric field is defined as, or the strength or the intensity of electric field is defined as the electrostatic force experienced by unit positive test charge kept at some definite point or kept at the specific point. So here this equation represents the direction of electric field always in the direction of electrostatic force, or we can get the value of electrostatic force is equal to Q, means this is the test charge which is kept in the electric field. This is the magnitude of the charge which is kept in the electric field, along with the sign. Since it is in the vector form, so we will place the sign as well. And E is the electric field. It also represents that the direction of electrostatic force on a positive charge, Q here is the positive, direction of electrostatic force or Coulombic force on a positive charge is always in the direction of electric field. Suppose that this is the direction of electric field and this is a positive charge Q kept in this field. So force experienced by this charge F is equals to Q into E, and the direction of force will be in the direction of electric field. This is the direction of electric field and this is the direction of force. What will happen if there is a negative charge? This is an electric field, E, direction is towards right. A negative charge is kept at this place. So what is the force on this negative charge? So force on this negative charge is, this is the Q is the magnitude value of the charge, minus is the nature of the charge, and E is the electric field. So the direction of force is, negative here represents opposite. In the vector equations, the negative sign represents the direction, opposite direction. So the Coulombic force or the electrostatic force on this charge minus q on this negative charge is opposite to the direction of electric field. Minus is representing opposite. So direction of force is opposite to the direction of electric field. That is, electric field is towards right direction and the force experienced by the charge is towards left. So remember, electric field every time apply a force on a charge. Now, C. Continuous but not closed. This is the field due to some system of charges. So if this is the direction is towards right, so certainly, as earlier discussed, the electric field lines starts from positive. So the positive charge or the system of positive plate or system of positive charges are towards the left, and this electric field line will travel till infinity. Similarly, if this is the electric field traveling towards right, so certainly this electric field will move and terminate somewhere. It will find negative charge. So this is negative charge, it will traveling towards negative. So where these charges are, where these electric field lines are coming from? These field lines are coming from infinity. Means due to a positive charge, electric field line will start and travel to the infinity if in between there is no other charge kept. If there is a negative charge, the electric field lines will terminate and they will start from infinity and they will come to the negative charge if there is no other charge kept in the path. Electric field cannot be closed curve. Like the magnetic field lines are continuous and closed, but electric field lines are continuous but not closed. So remember, this is a difference also between the electric field lines and the magnetic field lines, that electric field lines are continuous but not closed, but magnetic field lines are continuous and closed curve. So if I say this is the electric field line or pattern of electric field due to some charges or system of charges, so this is wrong. An electric field or field line cannot be a continuous curve, cannot be a closed curve. Now, if in the path of electric field, due to some charges or due to some system of charges, there comes a conductor. So what happens? As earlier told, inside the conductor net electric field is 0. So actually what happens there? So if this is some electric field due to some system of charges and in the path of the electric field there is a conductor. So these electric field lines will pass through the conductor as it is passing here. And earlier, as I told, that in the conductor there are the free electrons. So if this is a conductor, so certainly there are the positive and negative charges where the electrons are free. So this electric field will apply the force on the positive charge in its direction, but the same electric field will apply the force on the negative charge in the opposite direction. Therefore, the positive and negative charges inside the conductor will get separated. Positive charge will be forced in the direction of electric field and negative charge will be forced in the opposite direction of electric field. Thus, this separation of the positive and negative charge produces another electric field inside the conductor, which is known as induced electric field. Since the applied electric field and induced electric fields both are equal in the magnitude but opposite in the direction, therefore net electric field inside the conductor become 0. So if a conductor is kept in the path of electric field, so inside the conductor net electric field will be 0 and the electric field will continue from the further phase, from the opposite phase of the conductor. Now some other points about the electric field, representation of electric field. If the electric fields are represented by the parallel arrows which are equidistant, it means this is the uniform electric field. So this representation represent the uniform electric field, where the direction of electric field is constant as well as magnitude of the electric field is also constant. That is, at point X, the strength of electric field is equals to electric field at point Y. Both the points have the same electric field, that is uniform electric field. This is the representation of uniform electric field. Now what happens if the electric field lines are parallel, but the separation, that is the distance between these parallel lines, are not equal? They are not equally spaced. So here we will see this is the point A and this is the point B. Direction is constant, but the magnitude is not constant. As discussed earlier, the line density represents the strength of electric field at a point. So here at point A, the line density is more than that of at point B. That is, electric field intensity at A is more than electric field intensity at B. Since direction is constant but the magnitude is not constant, therefore this representation is an non-uniform field. Now just you see here the electric field lines are diverging, means direction is also changing as well as magnitude also changing. Now if I take 2 points X and Y, so very easily it can be seen that at point X the line density is more than that of Y. Therefore, electric field intensity at X is more than the electric field intensity at Y. So, this representation also goes into non-uniform electric field. So, if the electric field lines are parallel and equispaced, then this representation goes for the uniform electric field. If they are parallel but not equally spaced, then they are non-uniform, or if they are converging electric field lines or diverging electric field lines, then they also represent non-uniform electric field lines. So if we see about the electric field line due to a point charge, so just you see, these are the diverging one. Electric field lines due to a point charge represents that due to a point charge, electric field is not constant, non-uniform electric field. Similarly, due to a negative point charge, electric field is also non-uniform, and due to a system of positive and negative charges, or due to two identical charges, these are non-uniform electric field lines. But if somewhere this is the representation equally spaced in the same direction, so this is the uniform electric field. So thus we conclude the properties of electric field. In the next video we will see how to find the electric field strength at a point due to a point charge or due to some system of charges. By then, recall and revise the properties of electric field. Thank you.